Se siete tutti d'accordo, faccio anche una registrazione per avere un backup.
Okay. Non riesco a riconoscere la squadra del gagliardetto dietro di te.
È Asolo, è della Gran Fondo di Asolo.
Ok.
Siamo in diretta,
No.
prego.
Posso condividere lo screen?
Yes. Sì? Ok.
Okay,
As you want, you can start, and you have 20 minutes to present your final exam. Okay?
All right then. Is everything working?
Yes, perfect.
All right. So the main focus of this presentation will be on distributed optimization methods for speeding up the training of neural networks. The reason why we're interested in distributing the training is related to the fact that data sets are becoming very large and models are getting more and more complex, leading to, therefore, to training times that can be as long as multiple weeks, even when the hardware accelerators such as GPUs or TPUs are used. And in order to be able to train faster new models, we would like to decrease this training time by scaling the system horizontally, which means essentially using multiple workers cooperating to solve the same optimization problem. Throughout this work, we will use the concept of data parallelism, which means partitioning the training datasets between multiple workers, such that each node sees only a small fraction of the entire dataset, and therefore the training will be sped up. Okay, so before moving on with the presentation, I would like to introduce the work I did during my internship, which is what indeed pushed me into studying these topics. So we can find examples of big data problems in the context of high energy physics experiment at CERN, where hundreds of petabytes of data are produced each year. So there is a huge interest in integrating standard big data tools such as Apache Spark with the existing software to perform the analysis. And that indeed was the goal of my internship, where I built an end-to-end machine learning pipeline from ingesting data to the distributed training of the models. And this is based on the previous work done by some physicists. The work resulted to be quite interesting, and a paper describing it in details has been published a couple of days ago. However, we observed some limitation in the distributed training, especially when using standard methods and when we are running on general purpose hardware such as cloud. So I was interested in understanding how we can overcome these issues. Okay, so now we can introduce this problem for a more formal point of view. So we can imagine to have a network of M workers, each of them representing a computational node, having its local partition of data, as we mentioned at the beginning, and therefore a local loss function. Here, dy is representing the local distribution of data. And in the rest of the work, we will assume that the variance of the local data is small. That is, the distribution amongst all workers are similar. So we have that these M workers are cooperating to solve the same optimization problem, which is finding the model minimizing the average loss between nodes. And all the algorithms we will describe later will solve problems expressed in this form. So we have that the gradient of the function we are interested in minimizing is just the average of the gradient computed by every worker using the local data. So we can see that all the terms of this sum can be computed in parallel by each worker. So once we have computed this gradient, it can be used to update the model before moving to the next iteration. Okay, now with a slight abuse of notation, we will indicate the gradient of Fy with the stochastic gradient computed using only one sample. However, we know that this is true in expectation. So it is possible to prove that an upper bound for this kind of parallelization to the number of iterations needed to reach a stable solution is given by this quantity over here. For the sequential SGD, that is when using only one worker, we can prove that the convergence rate is 1 over square root of t. As with this kind of parallelization, we are m times faster, obtaining the speed up we were looking for. However, from a practical point of view, we need to aggregate the gradients from all the workers before computing the sum and before updating the model. And there are different possible ways of doing that. So now we will describe the idea behind two methods, and the practical implementation of it can be a bit more different and complex. So for example, the first one is using a parameter server, which stores the model parameters. So we have that each worker is using its local data to compute the gradients and then push it to the parameter server. Once the collector has received the gradients from all the workers, it can finally compute the sum and use it to update the model. The new model X prime is then pulled by the workers and a new iteration can begin. However, one weak point of this method is that the collector needs to receive the gradients from all the workers, and this may quickly become a networking bottleneck. For this reason, in recent years, methods allowing to aggregate gradients using collective operation without a central node are rising more and more interest. One such operation is called OReduce. In this operation, a target array is reduced in all processes, and the reduction can be, for example, a sum we are interested in computing. A common implementation of the OReduce used in deep learning is the ring OReduce. So let's try to give a hint on how it works. So we can imagine to start from node 1, which sends its gradient to node 2, which then adds its local gradient and sends it to the next node in the ring, so on and so forth. It will end up at the end of the ring as 4 in this case, which, as you can see, as 4 will contain the sum of all the gradients and can therefore be used to perform the update. This is just a schematic view. More efficient, the real implementation of this method is a bit different and much more efficient. Okay, this kind of idea is present also in many modern deep learning libraries, such as TensorFlow and Horovod and many others. So from now on, we will call OReduce STD the parallel STD implementation, where the gradients are aggregated using an OReduce operation. However, the main drawback of this strategy for parallelizing STD is that it introduces long idling time and a large communication time. This is because this is a fully synchronous method, which means that before moving to the next iteration, all workers must have finished computing the gradients. So when some nodes or the network are experiencing slowdown, the whole iteration will be slowed down. And that was indeed the issues I mentioned in the beginning, that we observed while performing the distributed training at CERN. So as we said, the reason for this is that a global synchronization is required because an exact average is performed at every iteration. So we can see that by imagining that every worker performs this local update. And then after this, all models are averaged. We see that the new model generated in this way has the same update rule as we have seen before. So again, the problem is that we are computing an exact sum, taking into account all the workers. Could we try to maybe break this global synchronization by approximating the average in order to decouple the system? And that's exactly what the decentralized method for parallelizing SGD do. So we can imagine to rewrite the previous sum in this way. And we see that there is this new term, Wij, and a pair of nodes communicates only if Wij is different than 0. Hence, we can in this way reduce the communication and decouple the system. If we set W equals to 1/m for every pair, we will fall back to the previous case of the OReduce. So in such way, the topology of the worker now is described by a graph where the vertices are computational nodes and edges are the active links at a certain iteration. And starting from this concept, we can build the different methods. One such method, the first one that we will describe, is called a synchronous decentralized parallel STD. And in this method, every iteration, one node communicates only with one neighbor node. So, okay, let's see a schematic view. Okay, we begin by reading the most recent model, which we call XAT from the memory of the worker. Then, in parallel, a stochastic gradient using this model and is computing at the same time. One peer is sampled, and the model of the worker I is averaged with the model of the neighbor j. So we can see that in such implementation, if computing the gradient is longer than the communication time, then the communication will be completely hidden by the computing time. Then finally, after having done that, we can compute the new model XAT by using the average model and the gradient we computed previously. So it is possible to prove that even by performing only pairwise averages, the convergence rate of this method is the same as the standard parallel STD, while we are hiding the communication and decoupling the global synchronization. The second method we introduced is called swarm STD. And here the communication time is reduced by performing multiple local updates before sampling one neighbor and averaging the model. So a schematic view is as follows. As we said, we perform each local updates of the models. Then we can sample one neighbor and average the two models. This then will become the new model for the next iteration. And also in this case, we can prove that the convergence rate is always the same as parallel STD. While once again, we are decreasing the communication time by performing these local updates. Okay, the last algorithm we introduced is actually a framework which can be used to improve the performance of other distributed optimizer by performing momentum-like updates. And this is called a slow momentum. The idea is the following. So we perform tau steps of a base optimizer, which can be, for example, the swarm STD we just introduced. D here is the search direction at worker I. And if the base optimizer is STD, for example, this will just be the gradient. Then after the tau iteration of the base optimizer, an exact average of all the models is computing. And then the resulting average model is used to compute the slow momentum update. Here, beta is the slow momentum factor. And once we have computed U, we can use it to perform the slow-mo iterate update. Okay, we have that the convergence depends by the base optimizer. In the thesis, starting from the results obtained by slow-mo and swarm, we computed the convergence rate for swarm STD and proved that once again the convergence rate is this quantity similar to the parallel STD. And this result is similar also to the ones obtained by slow-mo authors for other distributed optimizer. So, however, even though this exact average we mentioned is performed only every tau iteration, we would like to remove it if possible in order to not impact the scalability of the decentralized method we were analyzing. So we know that for the two decentralized method we have analyzed, at every step, this quantity is upper bounded, so it's small. And this is encoding the fact that all models are clustered around their mean, which indicates that they are sufficiently similar. So we can imagine to try to remove the average since they are already similar. And we observed that indeed, by removing the average, we are not impacting the performance, suggesting that all the benefits provided by this algorithm are caused by the momentum-like updates and not the fact that we are introducing this periodic average. So, okay, we can now perform some tests using the algorithm we have just described. I implemented everything using PyTorch and MPI for the communication between workers. The tests were performed on Cloud Veneto, which is a cloud hosted by INFN units in Padua and Legnaro National Labs. And this environment, as we will see later, will highlight the advantages of decentralized methods because the slowdowns of workers were very frequent. And all the tests have been performed using only CPUs. And one more note, in the practical implementation, the mini batch STD has been used instead of the plain STD with a mini batch which is ranging usually from 32 to 128 samples. So in this first test, the impact of communication has been measured. We use the LeNet model, a small convolutional network on the MNIST dataset, because here the computational time on CPU is comparable to the communication time. So to perform this test, we'll let the train run for 300 epochs just to have a nice samples to plot the distribution and measure, indeed in these 300 epochs, we measure the communication time and the total time for each epoch. As we can see, the communication time for the two decentralized method is lower than the one of our reduced SGD. And this translates into a lower training time. We can also measure the average time taken to compute one batch with respect to the number of workers, and see that the decentralized methods, in the decentralized method, the remains almost constant. This is because always a communication between a pair of workers in our algorithm is involved. And on the other hand, increasing the number of workers in the or reduced method increase the probability of having a slowdown on a node, and therefore causing a slowdown on the entire process. So if we look at the convergence with respect to time and number of epochs, we see that the decentralized methods converge faster with respect to both the number of epochs and training time. So as we will see later, this improvement in the validation accuracy is mainly due to the momentum. In appendix, we have also a similar benchmark for another standard dataset, which is training, for example, the residual network on CFR10. So now I would like to introduce the classification problem we had in the pipeline mentioned at the beginning of the presentation. Here, the goal was to train a classifier capable of recognizing free physics processes. In the datasets used for the training, there were 5 million rows, where each row is called events, and they correspond to the list of particles recorded by the detector. In particular, after the pre-processing, we have that each event is a list of 801 particles, and each of them is described by 19 features, encoding its kinematics and characteristics such as the charge. So each event can be viewed as a matrix 801 times 19. So from this dataset, we consider two different sub-datasets and classifier. In the first one, called the high-level featured dataset, every event is mapped into a set of 14 features, physics-motivated features, encoding the knowledge we have of that particular process. These features are classified and using a small feed-forward neural network. In the second one, called low-level feature, we try to avoid the step of creating the feature and use it directly the list of particles to perform the classification. And this is done by using a recurrent neural network like one. Yeah. So as we see in input, we have the sequence of particles, each of them with its feature like momentum, position, and so on. In this list, the first particle, this list of particles is always ordered in the same way in order to have a kind of series. And the first particles is always the same with a certain characteristics that is present in every event of this data set. And then all the others are sorted by increasing angular distance from it. So since the high-level feature classifier we just mentioned is a small model, the computer time here is small again, and therefore the impact of the communication is bigger, as we can see from the plot here on the right. If we look at the convergence with respect to the number of epochs, we see that the two decentralized methods combined with the momentum are obtaining a higher accuracy. And this improvement, again, is due to the momentum. Okay, so indeed, if we look at the performance of the method without the slow momentum, the blue line, we see that they are even worse than or reduced as the reduced SGD. So the slow momentum, even without having the average, is improving the performance without impacting the benefits in terms of communication times of the decentralized methods we were analyzing. So finally, we also performed the training of the low-level feature classifier on a subset of the original dataset containing around 70,000 events due to time constraint. As we can see, the final accuracy is reached faster in terms of number of epochs by methods using the slow momentum. Again, this improvement is due only to the slow momentum. Otherwise, it will be again worse than the reduced SGD. I believe that when using the full dataset, these methods will lead to a better final accuracy, as happened for the high-level feature classifier. Indeed, when training on the full dataset, a final accuracy of around 96% can be obtained, whereas here we have only around 94%, and this can be due to a lack of a training example. The impact of communication here is much lower, since the communication time for this kind of model is negligible with respect to the computational time, because the model was quite complex. And this, of course, will change if we use, for example, GPUs to compute big data. So, in conclusion, we described two recent proposed decentralized methods for the training of neural network. and a framework called Slow Momentum, which aims at improving the distributed optimizers using momentum-like updates. Then we perform different numerical tests where we analyze the scalability and the convergence on different data sets and problems. Moreover, we saw that slow-mo without the average isn't impacting the scalability. So future lines of work include understanding the role of the momentum in the distributed training, since as we saw, it can have a big impact, and actually prove that the average is not required to have the convergence. Thank you.
Okay, thank you very much for your presentation, Matteo. There is any question, comment?
I have a quick question.
Yes.
It's more, let's say, curiosity.
Mm-hmm.
What do you? Because I saw from the experiment that, and you, I mean, you covered this in several parts of the presentation, that you didn't do an experiment with GPUs. So,
no.
I mean, first of all, why? And second, do you think that since the architecture is the hardware architecture is definitely completely different, would you expect to see, especially on the distributed part, and also from the technical point of view, since you use OpenMPI and so on?
Okay.
Do you think that you get similar results or not?
Okay, so first of all, I didn't use GPUs because in the cloud Veneto where I performed the tests, there were only 4 GPUs, and they were all taken by the researchers doing their stuff, and I couldn't have them for let's say a couple of days, so all 4 of them. So that's the reason. But in the training that we performed at CERN, we performed indeed the training also on GPUs, the distributed part, on Oracle Cloud, for example. But over there, we just when I was doing my internship, we just let's say tested the standard methods. I didn't implement the stuff I studied now. So on the other side, okay, I got your question. I believe indeed that if GPUs are used, I could still have a benefit, because for this such implementation, okay, we have for the methods a computational thread and a communication thread. So the computation thread is just taking care of computing the gradients, while the communication is happening on another thread. So I think that if the computational speed up using, for example, the GPUs in the computational thread, this will end up speeding up everything, because, as I said, the problem when training large model, okay, for example, I can also see here for example, the residual network on C410, we see that here the difference is not as big as for other models, because if you have, for example, the computing, let's say a batch, I don't know, I throw a number, takes 5 seconds, while communicating takes just a couple of milliseconds, let's say 100 milliseconds, then on the overall training, this communication time will be, the impact of the communication time, again, is negligible with respect to the overall computational time.
Okay, thanks.
You're welcome.
Okay, thank you. There is other question, comments?
Can I make a question and one comment, please?
Yes.
Okay, so the question is, have you run any statistical analysis on the results that you obtain in any of the experiments? Because whenever I see an improvement of 0.2, 0.3%, it's hardly, it's not never, but it's hardly a statistical significant difference. So you're actually showing that you can perform as well as other state-of-the-art methods. So have you run any experimental, not experimental analysis, but statistical analysis on the difference of the results?
Wait, you mean in the result I shown? Okay,
yes,
maybe
yes.
I forgot.
The classification both in NIST and the high energy.
Okay. I forgot maybe to mention it, but these are not the result of one run. I mean, I performed 3 runs and average the result of these 3 runs, for example. I don't know if you you were meaning a more complex analysis, but I didn't do that.
I mean, yes, in the sense that maybe it's just by chance that you are getting the 0.1, 0.2 difference. Okay, it's just to see if there is.
Well, okay. I mean, I trained the models multiple times using different initial models by changing the seed, and I was always obtaining this kind of improvement, sometimes bigger, sometimes lower, and on average is this one.
Yes, I know, but there are methods to say exactly whether this is significant or not.
Okay. No, I didn't do that.
And this is one part. The comment is, since the difference is very small, and if you go, for example, right now on the documentation of the Keras API for deep learning that implements deep learning methods, you can see on the exact data set they perform, for example, 92%. So it's half a % better than what you show. So
I mean,
that's the point. So whenever it's so small, I would focus on the fact that you are improving the time part. So you can obtain the same effectiveness with probably half of the time that you, or the effort or the cost that you need.
Yeah, sure.
So that's the part I would focus on.
Okay. But one thing is that the comparison I wanted to bring here is that is compare these two new decentralized methods with the standard way of parallelizing SCD, which is the or reduce, and shown that with the momentum we are even able to match the final accuracy or even improve it. Of course, here we are not obtaining the state of the art accuracy, as you mentioned, because it can be again around also 91, 92%. But that's one. Okay, that's one trade-off that you have, because usually the more worker you add, the kind of less accurate you are. I mean, it requires really a good fine-tuning of the method in order to match the sequential case, how do I say, performance.
Okay, thank you.
You're welcome.
Okay, I think that it's okay. We can stop here. Now we take 5 minutes to discuss a little bit, and we come back to finish. Okay, with the final exam.
Should I wait?
See you
here?
later. You can stay.
Okay, thank you.
Ciao Daniele, se vuoi ripartire col live. Ciao Matteo, questa parte la facciamo in italiano, visto che la proclamazione potrebbe esserci un po' di parenti o qualcuno che vede, non...
Certo, certo.
Allora, aspettiamo di essere...
Confermo che siamo in diretta e possiamo procedere.
Perfetto. Allora, caro Matteo, abbiamo discusso un po', il periodo in cui stiamo vivendo tutti è quello che è, ma insomma questo tipo di proclamazioni e discussioni di laurea sono una delle cose che riusciamo ancora a fare nei migliori modi. Sono contento che tu abbia concluso i tuoi studi e la commissione ha discusso a lungo solamente per confermarsi nella sua valutazione e quindi procediamo alla proclamazione. Allora, non abbiamo tolto tempo, siamo un po' più informali rispetto al passato. Allora, dottor Matteo Migliorini, la commissione di laurea ha approvato la sua prova finale con la votazione di 110 su 110 e lode. Per l'autorità conferitami dal magnifico rettore, la proclamo dottore magistrale in Data Science. Complimenti.
Grazie mille a tutti.
Perfetto.
Congratulazioni.
Grazie.
Congratulazioni.
Congratulazioni.
Grazie.
Abbiamo il gomito invece che la mano.
Esatto, così.
Sì, idealmente.
virtualmente, esatto.
Adesso
Perfetto, allora buona continuazione, grazie a tutti e niente, buon futuro e buon tutto quello che deciderai
Grazie
di
mille.
fare.
Grazie mille.
Arrivederci.
Grazie.
Buona giornata a tutti.